continue our discussion further. So in the previous lecture we were looking at the design principles which have to be followed in constructing a larger discrete species, wherein the information is contained in the system already in terms of the ligand design, in terms of the metal design, and we proposed here different strategies. Now before we go into the actual systems, there are a couple of things we need to keep in mind. So firstly, when you have got a ligand can be monodentate, bidentate, tridentate, tetradentate, depending upon the number of donor atoms. So we can have multidentate ligands, or we can have monodentate ligands, which depends upon the number of donor atoms that can be given to a particular metal center. But here we refer to a new term which is referred to as topicity of a ligand, which is actually the number of distinct binding sites which are available in a ligand, and these are the number of distinct binding sites available in a ligand. And in this regard we can have monotopic, ditopic, tritopic ligands. Monotopic ligands have got only one binding site, and essentially these are the terminal ligands, and they can also serve as protecting groups on metals that form larger species. Then we can have polytopic ligands, which contains multiple, as I told you, this is the number of distinct binding sites available in the ligand. It contains multiple binding sites which enables the formation of complexes having more than one metal center. So multiple metals can be included in a polytopic ligand to form the resulting species having more than one metal center. And here therefore we refers, now as I told you that we use the word here N-topic, which refers to the number of the distinct binding sites, and this is not the number of individual donor atoms available for coordination. So this is a fundamental difference between denticity of a ligand and topicity of a ligand. So we can now look at the formation of first racks, ladders, and grid structures, and all the structures, they are closely related to each other because they consist of a regular array of metal ions which are joined by rigid, linear, and multidentate ligands. Rigid, linear, and multidentate ligands. So this is the construction blocks. This is the construction mode of formation of this rack, ladder and grids. Let us look at this process. So we can have where we can have a ligand backbone which is now called ditopic. Now why is it called ditopic? Because this is one distinct binding site, this is another distinct binding site. This particular binding site can have different kind of donor atoms. It can have 2 donor atoms, it can have 3 donor atoms, it can have 4 donor atoms. It can also have different kind of donor atoms, but essentially it is a ditopic ligand because it is called 2 distinct binding sites labeled 1 and 2. And this is a monotopic ligand. This is also monotopic ligand. It has got 1 binding site. Similarly, we can now understand the construction. So this is referred to as a 2 rack, where the number 2 refers to these number of rungs. It refers to the number of rungs which are attached, essentially referring to the 2 monotopic ligands which are attached to the ditopic ligand. Okay. So and you also have to keep in mind that these are arranged perpendicular to each other. These are arranged perpendicular to each other. So the ditopic ligands or the polytopic ligands run like this, and the monotopic ligands actually come and join at certain discrete nodal points where the coordination is completed, and they act as the rungs actually, and these are the monotopic ligands, and this bind at very specific sites to give you a rack like arrangement in a perpendicular fashion, to give you a 2 rack. Similarly, we can now have a similar arrangement where I can now extend the concept, where now I have a metal here, a metal here, a metal here, and we can have, now we can see, this is referred to as a 2.2 ladder, where this number 2 refers to the number of rungs, and this is a ditopic ligand. Now because it has got 2 coordination points, and we have got this also as a ditopic ligand, or it's a polytopic ligand. Now in this case it is ditopic. So, and how many such numbers are there? This is 1 and this is 1. So there are 2 such numbers, or the 2 numbers of polytopic ligands which are present. So this forms a 2-2 ladder, and then we can have a grid like structure where we have a metal sitting here, and now you can see when a metal is sitting here, we'll have one horizontal bar like this, and then there will be a vertical bar which will be below this. So below the plane is a vertical bar and above is a horizontal bar. So there are total, for example, say each point has got 2 coordination numbers, so total there are 4 coordination sites, or it is essentially topicity 1 for each. So overall we can see that this can form a 2.2 square grid. This is a 2.2 cross 2 square grid, and now you can actually have from here, you can actually now have from here a distortion of the square grid, a distortion of the square grid can give you a chiral grid, where you will have For example, you will have now, say you have this particular arrangement, you have this here and you have this here and you have so we can have this is the top, go from the bottom, and similarly here if it is from the bottom it will go to the top. So this will give a square grid. Okay, so it starts from the top but then it goes to the bottom. So this is top, this is bottom, this is bottom, this is top. This gives you a chiral grid. So at every point you have got top, bottom, top, bottom. So now so how do we start now creating this necessary structure? So first of all, the design principle was that we have used the ligand. Now the design can be applied to different molecules for the construction of these rack, laddered, square grid and chiral grid. So first let us see how it's originated. So first we start with this particular ligand which is called phenantholin, and here you can see that the number of donor atoms, that is the denticity, is 2, but the topicity is only 1. That is, only there is one distinct binding site here. This is the distinct binding site where the 2 nitrogen atoms can now bind to a metal, say for example a silver ion. And we can now consider another. So this is a convergent ligand, and now we can have another ligand, for example which is a bipyridine. This again has got donor atoms, so this has got topicity 1, and now we can combine it with AgL4 plus or CuL4 plus, where L is a monodentate ligand. So naturally the monodentate ligands will be displaced. The driving force will be the Chelet effect, where we form the rings, and it will form now so we have silver ion from here, and now this is a tetrahedral complex. So this will now form this will now be, so we will have the phenantholin ligand in this direction and this will come perpendicular. So you can see that the bipyridine ligand is now coming perpendicular to the phenantholin ligand, and thereby forming a distorted tetrahedral geometry. So this was the first example which was conceptualized, which essentially consists of a locking of the metal ion in via the 2 ligands in perpendicular orientation, and the concept was now to extend this arrangement by using a polytopic ligand instead of a monotopic ligand. So here you see this ligand has got only one specific site of binding, topicity is 1. If you can now extend this topicity to multiple domains or multiple specific sites, then this will form a polytopic ligand, and that can be used to now form the ladder like arrangement which can now self assemble in a to form much larger discrete species. And people have now extended this concept. You can also now take a slightly different environment. Now let us consider, you can also take so we can now take okay, so we can have this and this. This is a terpyridine. Now this is tridentate, but it is monotopic. because this is the only one specific distinct binding site where the metal ion can now come and bind. Okay, and because the denticity is 3 and the topicity is 1, we can now use any octahedral complex. Say we can take ruthenium 2 plus L6 octahedral complex, and this can now form the N. This is coming from there, and the perpendicular one will be. So again, this tridentate ligand is in this particular orientation. The other one comes perpendicular and forms forms this particular metal ligand complex, which has got the ligands in specific binding environment. So this is again the perpendicular binding, and this perpendicular binding gives rise to the octahedral, distorted octahedral geometry. Again, a very specific mode of recognition. So it is not necessary that you need to have an ideal octahedron with idealized geometry. You can have distorted variants, and the driving force is again metal ligand interactions which stabilize the much larger species which are formed from the ligands, and a metal ligand complex which has got these monodentate ligands or monotopic ligands which cannot dissociate and form much larger size species. So this concept was now extended. So this concept was now extended to generate, to start with. So we can now look at an example first of a 2 rack, and so what was done is that the concept was now extended to formation using this particular ligand. Okay. So now this is a very different kind of ligand. Now here you see this is having denticity 6 but topicity 2. So this is one region of binding, and this is the second region of binding, and so this is now, you can say this is now my polytopic ligand, and this can now complex with a ruthenium 2 plus, and here also it can combine with ruthenium 2 plus, and this is the perpendicular orientation. So this can give you a 2 rack. Okay. So basically this is this is a polytopic ligand, and this is the terpyridine. Okay, and this is a monotopic ligand. As we saw that the terpyridine here has got only, this is a terpyridine, it's monotopic, it has got only one binding site. So we use a monotopic ligand as per definition and a polytopic ligand to construct a 2 rack species, and actually the crystal structure, the X-ray crystal structure has been determined for this particular species, and it exactly resembles this particular arrangement, and then the counterions which have been observed which stabilize this large cation are BF4 minus, PF6 minus, and CF3 SO3 minus. Now we can extend this concept to ladders, and in case of ladders there are, in the case of ladder we have 2 polytopic ligands connected by a certain number of ditopic ligands. So you see here this was the ladder like arrangement. So we have this polytopic ligand and it is connected by the ditopic ligand here, and the nomenclature is represented in the form of 2.n, where n is the number of rungs and 2 refers to the two sides, at which the rungs connect. So you have got this polytopic ligand and you have got the two rungs which connect, and each rung is a ditopic ligand which such that both the sides connect to both the sides of the polytopic ligand. So we have this particular arrangement, and let us look at a specific example where this is satisfied. So this was considered in a system where we have the following arrangement of the ligand. This is nitrogen here, nitrogen here, nitrogen here, nitrogen here, nitrogen here, nitrogen here, and we have now added 3 equivalents of this particular ligand. pH, pH, pH. So we again have this is ditopic ligand, and this is a polytopic ligand, and we also now add in, because we are going to have, and how many such? We need 2 such to connect from both the sides of the ladder, and we need the 3 rungs. So we have 3 equivalents of these, and then we need a template. Template is very important. So now we need a Metal-Ligand to template this species. So we have a polytopic ligand and we have a ditopic ligand. We have to template them in a way that they come together and to form the thermodynamically stable discrete species. And we add now copper 1, because copper 1 forms tetrahedral complexes. And so now what happens is that we have the copper here, we have the copper here, we have the copper here, and this is going to bind with the nitrogen, right? And here you will see that it forms the disc-like arrangement. Okay, so we have this nitrogen here, and we also have the nitrogen here, also have the nitrogen here, we have this, and then this again can come from here, this again can come from here, this can form copper +1, and then we are going to have the same polytopic ligand on this side, which will coordinate with the nitrogens here. Okay, and then we'll have a similar arrangement of this here, and then a similar arrangement of this here. So this will form a nice ladder-like arrangement where the two sides, vertical sides, are the polytopic ligands, and the horizontal bars are the rungs, which are actually the ditopic ligands which connect from either sides. So this gives rise to a 2.3 ladder, where 3 is the number of rungs and 2 is the number of polytopic ligands. So we can form these kind of large arrays, and so the copper ion functions here as a template. And another very interesting example where you can even generate a larger ladder. For example, you can now use the same ligand which I mentioned in the previous case. So now you can use the same ligand and you can now modify the rung. So the rung can be modified as follows. We can now use this particular species. So we now have this as one topicity tree, this is another topicity, and this is another region. So this is a tritopic ligand. We have now got a tritopic ligand, and this can now complex with the copper ion three such ligands. So you will have one this side, one will be behind, and one will be on this side. So you will have these three vertical polytopic ligands, which will such that each binding site will satisfy the tetrahedral geometry with copper plus 1, and it will form a 3-3 ladder. It will now form a 3-3 ladder, and this you see is actually a disc like tritopic ligand. You have a disc like tritopic ligand, and the topicity is 3. This is a polytopic ligand. It now forms the 3-3 ladder. So these kind of species will be templated by copper ion, which forms tetrahedral building blocks and assembles these ligands, the polytopic ligand and the ditopic ligand, or with a certain number. For example, the total number of species here is 3 plus 3 plus 3 copper ions, 9 species. The self-assembling is a very specific way to form these kind of large discrete species. So this makes us realize that self-assembly processes are very, very interesting, and so we have looked at now essentially racks, ladders, and you can have other variations as well. Now in the next lecture we will look at a specific set of self-assembly systems which are called helicates, and take up some examples related to these as well. Thank you.